For nearly a decade, a significant portion of the astronomical community held onto a quiet, specific hope, one they rarely said out loud in public, but discussed constantly among themselves at conferences and in private correspondence. The hope that a nagging, persistent disagreement in their measurements of the universe's expansion would simply, eventually, turn out to be a mistake. Better instruments would come along, the thinking went, sharper data would arrive, and the discrepancy would quietly dissolve, the way so many promising anomalies in physics eventually do once enough additional scrutiny is finally applied. Then James Webb launched, gathered its first several years of data, and instead of making the problem disappear, it did something considerably more uncomfortable. It confirmed that the problem was real. Pale blue drift. The disagreement at the center of this story has a name astronomers use constantly now, almost with a kind of weary familiarity: the Hubble tension. And understanding why it has become one of the most seriously unsettling open problems in modern cosmology requires understanding exactly what it actually measures, and why two entirely different, entirely legitimate ways of measuring the same basic quantity keep stubbornly refusing to agree with each other. The quantity in question is called the Hubble constant, named after the astronomer Edwin Hubble, who in the 1920s made one of the most significant discoveries in the entire history of astronomy, that distant galaxies are, almost universally, moving away from us, and that the farther away a galaxy sits, the faster it appears to be receding. This relationship, now called Hubble's law, provided the first direct observational evidence that the universe itself is expanding, every point within it moving away from every other point. Not because galaxies are flying through some fixed, unchanging space, but because the space between them is itself continuously stretching, carrying galaxies apart the way raisins in a rising loaf of bread are carried apart from each other as the dough itself expands, without any individual raisin actually moving through the dough on its own. The Hubble constant describes the specific rate of that expansion, how quickly the universe is stretching apart at the present moment, and pinning down its exact value has occupied astronomers for the better part of a century, because that single number carries enormous weight for nearly everything else cosmologists understand about the universe, including its age, its ultimate size, and the detailed physics governing how it evolved from its earliest moments into the vast, structured cosmos we observe today. There are, broadly speaking, two fundamentally different methods astronomers use to measure this constant, and it's the persistent, growing disagreement between these two methods, rather than any single flawed measurement, that constitutes the actual heart of the Hubble tension. The first method, often called the local or distance ladder approach, works its way outward from our own cosmic neighborhood, building a careful, step-by-step chain of distance measurements to progressively more distant objects, each step calibrated against the one before it. This method relies heavily on a specific class of star called Cepheid variables, stars that pulse in brightness with a very precise, predictable rhythm directly tied to their actual, intrinsic luminosity, a relationship discovered in the early 20th century by the astronomer Henrietta Leavitt, whose careful, painstaking cataloging of thousands of these stars provided astronomy with one of its most valuable and most enduring distance measuring tools. Because a Cepheid's pulsation period reveals its true brightness, comparing that true brightness to how dim the star actually appears from Earth allows astronomers to calculate, with real precision, exactly how far away it sits. By identifying Cepheid variables in progressively more distant galaxies, and combining those measurements with a second class of extraordinarily bright, similarly predictable events called Type Ia supernovae, exploding stars whose peak brightness follows its own reliable, well-understood pattern, astronomers have built an extended distance ladder reaching from our own galactic neighborhood out to galaxies hundreds of millions of light-years away, precise enough to calculate the Hubble constant directly from real, measured distances and real, measured recession velocities. The most careful, most rigorously refined version of this local measurement, led for years by the astronomer Adam Rees and his collaborators, has consistently produced a value for the Hubble constant hovering right around 73 kilometers per second per megaparsec, a number that describes, in the specific units cosmologists use, how much faster a galaxy appears to recede for every additional unit of distance separating it from us. The second method takes an entirely different approach, working backward from the very beginning of the universe rather than outward from our own local neighborhood. It relies on extraordinarily precise measurements of the cosmic microwave background, the faint, ancient afterglow of radiation left over from roughly 380,000 years after the Big Bang, the earliest moment at which light was finally able to travel freely through the universe, rather than being constantly scattered by the hot, dense plasma that filled all of space before that point. This afterglow, first detected accidentally in 1965 and mapped with steadily increasing precision by a succession of dedicated space missions since, carries within it an extraordinarily detailed, extraordinarily rich record of the early universe's exact physical conditions, tiny variations in temperature and density scattered across the sky that encode, if you know how to read them properly using the well-tested equations of modern cosmology, essentially everything about how the universe has evolved since that ancient moment, including, when combined with the standard cosmological model those same equations describe, a predicted value for exactly what the Hubble constant should be today. The most precise version of this measurement, produced by the European Space Agency's Planck satellite mission, which spent years mapping the cosmic microwave background with extraordinary sensitivity before completing its operations in the mid-2010s, arrived at a Hubble constant value of approximately 67 kilometers per second per megaparsec, a number calculated not by directly measuring nearby galaxies at all, but by extrapolating forward from the earliest moments of the universe using a physical model that has otherwise proven repeatedly successful at explaining nearly everything else astronomers observe about the cosmos. 67 versus 73. On the surface, that might not sound like an enormous discrepancy, a difference of roughly 9% between two independently measured values for the same fundamental constant. But in the extraordinarily precise, statistically rigorous world of modern cosmology, where both measurements have been refined and cross-checked so thoroughly that their individual margins of error have shrunk dramatically over the past decade, a 9% gap that refuses to close, and has, if anything, grown slightly more statistically significant as both measurement techniques have improved, represents something genuinely alarming. It suggests that either one of the two measurement methods contains some subtle, still unidentified systematic error, or, considerably more unsettling, that the standard cosmological model itself, the extraordinarily successful mathematical framework describing the universe's contents, its expansion history, and its fundamental physics, is somehow, in some specific but still unidentified way, incomplete. Astronomers, being appropriately cautious scientists trained specifically to distrust exciting anomalies until they've survived every reasonable attempt to explain them away, spent the better part of the 2010s hunting seriously for exactly this kind of systematic error, hopping, quite openly, to eventually find it. Nobody wanted the tension to be real. A confirmed, genuine crack in the standard cosmological model, a framework that has otherwise proven remarkably successful at explaining everything from the detailed pattern of the cosmic microwave background to the large-scale distribution of galaxies across the observable universe, would represent a genuinely significant, genuinely disruptive scientific problem, the kind that doesn't simply add an interesting footnote to existing textbooks, but potentially requires rewriting substantial portions of them. The most obvious place to look for a hidden error was the local distance ladder measurement itself, since it relies on a longer, more complex chain of individual calibration steps than the cosmic microwave background method, each one a potential point where some subtle, systematic bias could creep in undetected. Researchers scrutinized every link in that chain with extraordinary care. Could Cepheid variables in distant galaxies be subtly contaminated by light from nearby, unrelated stars, artificially skewing their measured brightness and therefore their calculated distance? Could the specific method used to calibrate Type Ia supernovae contain some overlooked systematic bias? Could the assumed properties of the Milky Way's own local environment, used to establish the very first rung of the entire distance ladder, be subtly different from what researchers had long assumed, throwing off every subsequent measurement built on top of that initial calibration? Each of these possibilities was investigated seriously, repeatedly, by multiple independent research teams over the following years, and each time, the careful hunting failed to identify an error large enough to actually explain away the tension. If anything, each round of increasingly careful scrutiny tended to slightly strengthen confidence in the original local measurement, ruling out one potential systematic error after another, without ever finding the specific flaw that would have allowed the entire uncomfortable problem to quietly resolve itself. This is precisely the state cosmology found itself in by the time James Webb finally launched in December of 2021, an entire field of extraordinarily careful, extraordinarily well-trained scientists, having spent the better part of a decade hunting for a mistake they genuinely hoped to find, and having instead mostly succeeded only in ruling out one plausible explanation after another, leaving the tension standing, increasingly confirmed, increasingly uncomfortable, and increasingly resistant to any simple, reassuring resolution. Webb represented, for many researchers working on this specific problem, the best remaining hope for finally settling the question one way or another, precisely because its extraordinary sensitivity and precision offered a genuine opportunity to test the local distance ladder measurement using an entirely independent method, one capable of cross-checking the Cepheid variable technique that had, by that point, become the primary focus of lingering suspicion within the broader astronomical community. That independent method involved a considerably different, and in several important ways considerably simpler, class of star than the Cepheid variables the field had relied on for decades. Called the tip of the red giant branch method, it takes advantage of a specific, well-understood point in an aging star's life cycle, the moment when a star of a particular mass, having exhausted the hydrogen fuel in its core, undergoes a specific internal transition that causes its brightness to peak at a remarkably consistent, predictable value, almost regardless of the individual star's precise age or composition. Because this peak brightness varies so little from one star to another, astronomers can use it as what's sometimes called a standard candle, an object whose true brightness is known well enough in advance that comparing it to how dim the star actually appears reveals, with real precision, exactly how far away it sits, functioning as an entirely independent cross-check on the distances calculated using Cepheid variables in the very same galaxies. Before Webb, this method had already been used with earlier telescopes, including Hubble, and had produced results sitting in an intriguing, somewhat ambiguous middle ground, generally supporting a lower Hubble constant value than the Cepheid method, closer to, though not perfectly matching, the value derived from the cosmic microwave background, work led prominently by the astronomer Wendy Friedman and her collaborators. This created a genuinely interesting scientific tension of its own, entirely separate from the main Hubble tension story. Two different teams of extremely careful, extremely well-respected researchers, using two different techniques, arriving at values that didn't perfectly agree with each other, adding yet another layer of uncertainty to an already uncertain picture. Webb's extraordinary infrared sensitivity and its considerably sharper resolution compared to earlier space telescopes made it uniquely capable of finally applying both methods, Cepheid variables and the tip of the red giant branch technique, to the very same galaxies, observed with the very same instrument, under the very same observing conditions, eliminating an entire category of potential systematic differences that might have been quietly contributing to the earlier, more ambiguous disagreement between the two techniques. If Webb's data showed the two methods finally converging on a similar value, once observed with identical, extraordinarily precise instrumentation, and if that converged value still sat noticeably higher than the cosmic microwave background prediction, it would represent about as strong a confirmation as the field could realistically hope for, that the local measurement itself was solid, and that the true source of the tension lay somewhere else entirely. Most likely within the standard cosmological models, own underlying assumptions about the universe's fundamental physics. That is essentially, in careful, precise terms, exactly what happened. In 2023, and continuing through subsequent observations, Adam Rees and his collaborators used James Webb specifically to reobserve galaxies already studied using Hubble, applying both the Cepheid variable technique and the tip of the red giant branch method side by side, using identical instrumentation to directly, rigorously test whether the Cepheid-based distances might have been subtly overestimated due to crowding or contamination from unrelated nearby stars. The specific lingering concern that had remained the most plausible candidate for a hidden systematic error throughout the preceding decade of careful scrutiny. Webb's sharper resolution confirmed that this specific concern, while a reasonable and responsible thing to have investigated so thoroughly, was not the source of the problem. The Cepheid measurements held up. Distances calculated using the tip of the red giant branch method, observed with Webb's superior precision, converged closely with the Cepheid-based distances in the very same galaxies, and the resulting Hubble constant value calculated from this newly strengthened, cross-validated local measurement remained firmly, stubbornly elevated, sitting close to that same uncomfortable 73 kilometers per second per megaparsec figure that had been standing, essentially unmoved, for the better part of a decade. That confirmation, arriving from the very instrument so many researchers had quietly hoped might finally dissolve the whole uncomfortable problem, instead accomplished something close to the opposite. It closed off the most plausible remaining explanation for why two careful, independent measurements of the same fundamental constant kept refusing to agree, leaving behind a considerably more unsettling possibility standing largely alone, that the standard model cosmologists have relied on for decades to describe the universe's contents, its expansion history, and its underlying physics, might itself be missing something, some ingredient or mechanism not yet accounted for, quietly distorting one of these two measurements in a way no amount of careful instrumental scrutiny could ever hope to catch, because the flaw would live not in the telescope or the method, but in the physics itself. Physicists working on this problem have spent the past several years exploring exactly what kind of missing ingredient could plausibly explain a discrepancy this specific, this persistent, and this thoroughly resistant to every attempt at finding a simpler, more mundane explanation. And the candidate solutions currently under serious consideration reach into some of the strangest, least understood corners of modern cosmology. The most actively discussed category of solution involves something researchers call early dark energy, a hypothetical modification to the standard cosmological model proposing that dark energy, the mysterious force responsible for driving the universe's present-day accelerating expansion, might not have behaved as a simple, constant, unchanging quantity throughout the entire history of the universe. The assumption baked into the standard model currently used to interpret the cosmic microwave background. Instead, early dark energy models propose that some additional, temporary burst of this repulsive energy may have briefly appeared during a specific, narrow window very early in cosmic history, sometime before the universe was even 100,000 years old, adding a short-lived extra push to the expansion rate during that particular era, then fading away again, leaving no obvious trace in the later universe except for its specific, lasting effect on how the size of the universe at that early moment relates to its size today. This kind of temporary modification, if real, would specifically alter the cosmic microwave background-based calculation of the Hubble constant, since that calculation depends heavily on precisely understanding the universe's exact expansion history all the way back to that early era. A brief, extra episode of accelerated expansion at just the right early moment could shift the calculated value derived from the cosmic microwave background upward, moving it closer to the higher value astronomers keep measuring locally, without requiring any change at all to the local distance ladder measurements themselves, which Webb had already worked so hard to confirm and strengthen. Several research teams have built detailed mathematical models testing exactly this idea, and the results have been genuinely, if cautiously, encouraging. Early dark energy models can be tuned to successfully close a meaningful portion of the gap between the two competing Hubble constant measurements, without disrupting the standard model's otherwise excellent agreement with numerous other, independent cosmological observations. That success comes with its own significant caveat, though one honest researchers in this field are careful to acknowledge clearly. Introducing early dark energy requires adding an entirely new, currently unobserved physical ingredient to the standard cosmological model, one whose specific properties, how much energy it briefly contributed, exactly when it appeared, and exactly why it faded away again so precisely, have to be carefully tuned, almost by hand, to match the observed data, rather than emerging naturally from some deeper, independently motivated physical theory. Physicists have a specific, somewhat uncomfortable term for this kind of solution, describing it, often with a note of genuine unease, as requiring fine-tuning, a pattern that has, throughout the history of physics, sometimes pointed toward a genuinely new discovery, and sometimes turned out to be an early, overly specific patch applied to a problem whose true solution turned out to be something else entirely. A second major category of proposed solution focuses not on dark energy, but on dark matter, the separate, equally mysterious substance believed to make up the overwhelming majority of all matter in the universe, detectable so far only through its gravitational influence on galaxies and galaxy clusters, never directly observed in any laboratory despite decades of dedicated search efforts. Some researchers have proposed that dark matter might not behave in quite the simple, inert way the standard cosmological model currently assumes, that it might, under certain specific conditions in the early universe, have interacted with itself, or with ordinary matter, in ways not currently accounted for, subtly altering the universe's early expansion history in a manner similar to, though mechanically distinct from, the early dark energy proposals. These interacting dark matter models remain, if anything, even less settled and less thoroughly tested than the early dark energy proposals, in part because they require making specific assumptions about dark matter's fundamental particle nature, something physicists still don't understand with any real certainty despite decades of dedicated experimental effort to directly detect dark matter particles in laboratories on Earth. Without knowing what dark matter actually is at a fundamental level, proposing specific new interactions it might undergo remains, by necessity, considerably more speculative than the already speculative early dark energy proposals, though several research groups continue actively developing and testing these ideas against the growing body of precision cosmological data. A third, considerably more radical possibility, one that a smaller but genuinely serious portion of the physics community continues to take seriously, questions something even more fundamental than dark energy or dark matter individually, whether the equations of general relativity themselves, Einstein's foundational theory of gravity, might require some subtle modification at the enormous scales relevant to cosmology. A scale far beyond anything general relativity has ever been directly tested at with the same precision achieved in our own solar system, or in the study of gravitational waves from colliding black holes. Modified gravity theories of this kind have existed in various forms since at least the 1980s, originally proposed as alternative explanations for the gravitational effects normally attributed to dark matter, and several researchers have explored whether carefully constructed modifications to general relativity's equations might also help resolve the Hubble tension, potentially addressing both mysteries simultaneously through a single, unified change to how gravity itself behaves across the largest scales of the cosmos. This particular avenue remains the most controversial among the three broad categories currently under serious discussion, precisely because general relativity has proven itself, across more than a century of increasingly precise testing, to be an extraordinarily successful, extraordinarily well-confirmed theory in every regime physicists have so far managed to test it indirectly. From the precise orbit of Mercury that first confirmed Einstein's theory back in 1915, to the extraordinarily precise measurements of gravitational waves detected from colliding black holes and neutron stars over the past decade. Proposing that this theory requires modification at cosmological scales carries a correspondingly high scientific burden of proof, one that modified gravity researchers acknowledge openly, continuing to develop and test their specific proposals against the ever more precise flood of cosmological data becoming available, while remaining, for now, a minority position within the broader field. There is a fourth possibility, one that some researchers find, in a strange way, the most quietly unsettling of all the options currently on the table, precisely because it doesn't require any dramatic new physics at all. It simply asks whether the standard cosmological model, despite its otherwise excellent track record, might be built on a foundational assumption that happens to be subtly wrong in some way nobody has yet correctly identified, some detail about the early universe's composition, or the precise physics governing how sound waves propagated through the hot, dense plasma filling the universe before the cosmic microwave background was released, that current models simply haven't gotten quite right, without necessarily requiring anything as dramatic as an entirely new form of energy or a modification to gravity itself. This possibility is, in some ways, both the most conservative and the most frustrating option available to researchers, because it doesn't point toward any single, specific, testable new physical mechanism the way early dark energy or modified gravity do. It simply suggests that somewhere within the admittedly enormous complexity of the standard cosmological model's underlying physics, a genuine, if currently unidentified, error exists, one that future theoretical work or future observational data might eventually reveal, without anyone currently being able to say exactly where to look for it or what shape it might ultimately take. What makes the entire situation genuinely, scientifically significant, rather than simply an interesting but ultimately minor technical dispute confined to specialists, is the sheer breadth and consistency of the evidence supporting the tension's reality. This isn't a single measurement disagreeing with a single theoretical prediction. It's an entire, carefully cross-validated body of independent local measurements, Cepheid variables, the tip of the red giant branch method, type Ia supernovae, and in more recent years, several additional independent distance measuring techniques developed and tested specifically to provide further cross-checks, all converging on a similar elevated value for the Hubble constant, standing in persistent, statistically significant disagreement with the value calculated from the cosmic microwave background, a disagreement that has, if anything, grown slightly more statistically robust as both sides of the measurement have continued to improve in precision over the past several years, exactly the opposite of what you'd expect to see if the tension were simply an artifact of insufficiently precise, insufficiently cross-checked data. Several major international research collaborations have been formed specifically to continue attacking this problem from multiple independent angles simultaneously, developing entirely new observational techniques capable of measuring the Hubble constant through methods that don't rely on either Cepheid variables or the cosmic microwave background at all. Hopping that a genuinely independent third method might help clarify which of the two existing measurements, if either, actually contains the hidden flaw responsible for the discrepancy. One such method, called gravitational wave standard sirens, uses the precise, extraordinarily well-understood physics of gravitational waves emitted by colliding neutron stars to calculate distances directly, offering, in principle, a measurement technique built on an entirely different physical foundation than either of the two existing methods, one that doesn't rely on the complex, multi-step calibration chain the traditional distance ladder requires, and doesn't depend on the detailed assumptions about early universe physics the cosmic microwave background method relies on. Early results from this gravitational wave method, based on the still relatively small number of suitable neutron star merger events detected so far by gravitational wave observatories, have proven genuinely useful, though not yet precise enough, given the limited number of qualifying events currently available, to definitively settle the tension one way or the other. As gravitational wave detectors continue improving in sensitivity, and as astronomers accumulate a larger catalog of suitable merger events to study, researchers in this field expect the standard siren method to eventually provide a genuinely independent, genuinely decisive third measurement, one capable of finally indicating, with real statistical confidence, which of the two existing, stubbornly disagreeing measurements more accurately reflects the true expansion rate of the universe. Or, in the more genuinely unsettling scenario, several researchers have begun to seriously entertain, confirming that both measurements are, in their own respective ways, correct, and that the true explanation lies not in either measurement being flawed, but in the standard cosmological model itself requiring the kind of genuine, currently unidentified revision the early dark energy and modified gravity proposals represent early, still unproven attempts to provide. Beyond these three major categories, researchers have proposed a range of additional, somewhat less widely discussed possibilities, including the idea that dark energy strength might not be perfectly constant even in the present-day universe, gradually evolving over cosmic time in ways the standard model's simplest assumptions don't currently account for, and even more exotic proposals involving the possible existence of additional, undiscovered particle species active in the early universe, contributing subtly to its overall expansion rate in ways current models don't include. Each of these ideas has its own dedicated research community, its own specific mathematical framework, and its own particular strengths and weaknesses when tested rigorously against the growing body of precision cosmological data astronomers continue accumulating. What makes evaluating all of these competing proposals so genuinely difficult and so genuinely slow-going is the sheer number of independent, precisely measured cosmological observations any successful solution now has to satisfy simultaneously. The standard cosmological model isn't simply built around explaining the Hubble constant. It successfully accounts for the detailed statistical pattern of temperature variations across the cosmic microwave background, the large-scale distribution of galaxies and galaxy clusters observed throughout the universe, the precise abundance of light elements like helium and lithium produced during the earliest few minutes after the Big Bang, and numerous other, independently measured cosmological quantities, all fitting together with remarkable, genuinely impressive consistency. Any proposed modification capable of resolving the Hubble tension has to accomplish that specific task without disrupting this much larger, much more extensive web of successful agreement between theory and observation, a genuinely demanding constraint that has, so far, prevented any single proposed solution from emerging as a clear, broadly accepted front runner. This is precisely why the field currently finds itself in a genuinely uncomfortable, genuinely unresolved position, one considerably more unsettling than simply having a single, clean anomaly waiting for its inevitable, eventual explanation. Cosmologists are not simply waiting for more data to arrive and settle the question, the way researchers studying that CERN penguin decay anomaly discussed on another evening are patiently waiting for additional collision data. The relevant data in this specific case has already arrived repeatedly from multiple independent instruments and multiple independent measurement techniques, and it has consistently, stubbornly refused to resolve itself into a single, comfortable answer. What's missing isn't more data. It's the correct theoretical framework capable of properly interpreting the data that already exists, a genuinely different, and in some ways more difficult, kind of scientific problem to solve. That difficulty connects directly to something worth sitting with honestly, in these last few minutes before we let this particular thread rest, a genuine humility that has settled over a field that, only a couple of decades ago, seemed to many observers to be approaching something close to a finished, settled picture of cosmic history. The standard cosmological model earned its name and its widespread acceptance precisely because it succeeded, repeatedly, at explaining an enormous range of independent observations using a comparatively simple, elegant mathematical framework, requiring only a small handful of fundamental parameters to fit an extraordinary wealth of data gathered from across the entire observable universe. The Hubble tension represents the first serious, sustained crack in that otherwise remarkably successful picture, a crack researchers spent a full decade hopping would simply seal itself shut once better instruments arrived, and which James Webb, instead of sealing, has helped confirm as genuinely, stubbornly real. That confirmation reaches beyond the specific technical question of exactly how fast the universe is expanding today. It touches something deeper, and in its own way, considerably more significant, the growing recognition among cosmologists that the framework they've relied on for decades to describe the entire history and structure of the universe, from its earliest moments through to the galaxies and stars we observe tonight, may be missing something fundamental, some piece of physics not yet identified, not yet understood, quietly distorting our picture of cosmic history in a way that has taken the most precise instruments human beings have ever built simply to notice clearly enough to take seriously. That missing piece of physics, whatever it eventually turns out to be, carries consequences reaching well beyond the specific technical question of the expansion rate itself, touching directly on some of the most basic, foundational numbers cosmologists use to describe the universe as a whole, numbers that depend, more directly than most people realize, on exactly which value for the Hubble constant turns out to be correct. The age of the universe itself sits near the top of that list. Cosmologists calculate this figure by running the universe's expansion history backward, using the standard cosmological model's equations to determine how long it would take, starting from an initial, extraordinarily hot and dense state, for the universe to expand to its currently observed size, at its currently observed rate. Because the Hubble constant describes exactly how fast that expansion is currently proceeding, a different value for that constant produces a genuinely different calculated age. The commonly cited figure of approximately 13.8 billion years, familiar from years of popular science coverage, is calculated using the lower, cosmic microwave background-derived value for the Hubble constant, the one hovering around 67 kilometers per second per megaparsec. If the higher, locally measured value of 73 turns out instead to be the truly correct figure, the calculated age of the universe shifts meaningfully younger, closer to 12.5 billion years, a difference of well over a billion years, a genuinely significant discrepancy for a number many people assume has been settled with far more precision and far more certainty than the current state of this unresolved tension actually allows. This connects, in a way worth sitting with directly, to another thread explored on a separate evening together, the story of James Webb finding galaxies that appeared, according to the Standard Model's timeline, impossibly bright and impossibly structured for how early in cosmic history they seem to exist. Some researchers studying that separate puzzle have begun wondering, carefully and speculatively, whether a resolution to the Hubble tension might end up connecting to that earlier mystery as well, since any modification to the Standard Model capable of explaining the discrepancy in the expansion rate would likely also alter, in some way, the calculated timeline for how quickly structure was able to form in the early universe. Nothing about this potential connection has been confirmed or seriously established yet, and researchers working on each puzzle individually remain careful not to overstate the link. But the possibility that these two separately discovered anomalies, one involving the universe's overall expansion rate and one involving the surprising brightness of its earliest galaxies, might eventually turn out to share a common underlying cause. Some single piece of missing physics responsible for both puzzles simultaneously represents exactly the kind of genuinely exciting, genuinely uncertain possibility currently occupying a meaningful portion of the cosmology community's attention. Beyond the universe's calculated age, the exact value of the Hubble constant also directly affects astronomers' understanding of the universe's ultimate fate, its size at any given moment in cosmic history, and even the precise calibration used to interpret nearly every other cosmological distance measurement astronomers currently rely on, since so many of those measurements are, directly or indirectly, built on top of assumptions about the universe's overall expansion history. A persistent, unresolved discrepancy in a foundational number this central to the entire field doesn't remain neatly contained within a single narrow question. It ripples outward, introducing a corresponding layer of uncertainty into an enormous range of otherwise carefully calculated cosmological quantities, a genuinely uncomfortable situation for a field that has spent decades working to reduce exactly this kind of uncertainty through ever more precise instrumentation and ever more careful measurement technique. In recent years, researchers have begun developing an entirely third, independent method for measuring the Hubble constant, one that doesn't rely on either Cepheid variables or the cosmic microwave background at all, offering hope for eventually providing a genuinely fresh, independent perspective on which of the two existing measurements, if either, is closer to correct. This method relies on gravitational waves, the ripples in spacetime itself first directly detected in 2015, produced by some of the most violent events in the universe, colliding black holes and colliding neutron stars. When two neutron stars merge, the resulting collision produces not only gravitational waves, but also, in at least some cases, a detectable burst of light across multiple wavelengths, allowing astronomers to independently measure both the exact distance to the merging pair, calculated directly from the physical properties of the gravitational wave signal itself, and the exact recession velocity of the galaxy hosting the event, measured through more conventional means. Researchers have given this technique a specific, evocative name, calling these merger events standard sirens, deliberately echoing the standard candle terminology long used to describe distance measuring techniques like type Ia supernovae and the tip of the red giant branch method. The very first standard siren measurement, derived from a neutron star merger detected in 2017 and observed simultaneously across gravitational wave and traditional telescope observations in a landmark, genuinely unprecedented collaborative astronomical effort, produced a Hubble constant estimate sitting, intriguingly, in a broad range that didn't clearly favor either the higher local value or the lower cosmic microwave background value. Though the measurement's uncertainty at the time remained too large to meaningfully settle the disagreement one way or the other. Since that initial detection, researchers have continued refining this technique, and as gravitational wave detectors around the world continue improving in sensitivity, and as astronomers gather a larger sample of these rare, valuable merger events, many in the field hold real hope that standard sirens will eventually provide the kind of genuinely independent, genuinely decisive third measurement capable of finally indicating, with real confidence, which of the two existing measurement methods, if either, has been correctly capturing the universe's true expansion rate all along. There's something worth appreciating in the sheer variety of independent techniques cosmologists have now brought to bear on what looks, from the outside, like a fairly narrow technical question: the precise rate at which the universe is expanding. Cepheid variables, pulsing with a rhythm tied directly to their own intrinsic brightness. The tip of the red giant branch, a specific, predictable moment in an aging star's internal transition. The ancient, faint afterglow of light released 380,000 years after the Big Bang, still detectable, still measurable, drifting across the entire sky in every direction. And now, ripples in the fabric of spacetime itself, produced by some of the most violent collisions the universe is capable of producing, carrying within their specific pattern a direct, independent measure of cosmic distance that requires no calibration against any other technique at all. Four entirely different physical phenomena, studied using four entirely different categories of instrument, all aimed at answering the exact same fundamental question. And the fact that three of these four methods currently disagree in a specific, consistent, statistically significant way tells you something genuine and important about the current, honest state of humanity's understanding of its own universe. That state is neither the comfortable, fully settled picture many people outside the field assume modern cosmology has already achieved, nor is it a crisis threatening to unravel everything astronomers have carefully built over the past century of dedicated observation and theory. It sits somewhere considerably more interesting than either of those two extremes, a genuinely open, genuinely unresolved question, sitting right at the edge of what current instruments and current theory can actually determine with confidence, precisely the kind of question that tends, historically, to eventually lead toward exactly the sort of genuine, significant scientific progress that later gets remembered as a meaningful turning point, once enough additional time and enough additional careful, patient research has finally passed. Researchers working on this problem have been notably candid, in interviews and public lectures over the past several years, about roughly how long they expect this particular chapter of the story to remain genuinely open. Adam Rees himself, whose careful, decade-spanning work on the local distance ladder measurement has sat at the very center of this entire story, has spoken publicly about the tension not as a temporary embarrassment waiting to be quietly resolved, but as a genuine, exciting scientific puzzle, one he has described as likely representing new physics rather than any remaining measurement error. A striking, notably confident statement from the very researcher, whose own measurements first helped establish the discrepancy as real in the first place. That kind of confidence, expressed publicly by someone with such direct, personal stakes in the outcome, carries real weight within a field otherwise defined by careful, measured caution about overstating any single result. Wendy Friedman, whose independent work using the tip of the red giant branch method has provided some of the most important cross-checks in this entire story, has struck a somewhat more measured public tone, continuing to emphasize the importance of further refining and cross-checking the local measurements, even as Webb's data has strengthened confidence in their overall reliability, a genuinely valuable, complementary form of scientific caution operating alongside Rees's more confident public statements, together representing exactly the kind of healthy, ongoing internal debate that characterizes a field still genuinely working through an unresolved, significant problem, rather than one that has already quietly settled on a single, agreed-upon answer behind closed doors. That ongoing, unresolved debate is where this particular thread of tonight's story currently rests. 4 independent measurement techniques, 3 of them converged into an increasingly confident, increasingly precise agreement. One of them, the ancient light of the cosmic microwave background, standing apart, equally precise, equally well confirmed, and equally unwilling to budge, waiting for whichever piece of missing physics eventually turns out to bridge the gap between the universe as it existed 380,000 years after its own birth, and the universe as it actually appears to be expanding today, 4 billion years, or perhaps closer to 2.6 billion years, before any of us were ever born to notice the discrepancy at all. That discrepancy, 4 billion years versus something closer to 2.6 billion years before any of us existed to measure it, represents, in its own quiet way, one of the more genuinely humbling admissions modern science currently has to offer, a reminder that even a framework as successful, as thoroughly tested, and as widely trusted as the standard cosmological model can still harbor a genuine, unresolved crack. One so subtle that finding it required building and launching some of the most sophisticated scientific instruments human civilization has ever produced, and even then, required nearly a full decade of patient, careful, repeated measurement before the astronomical community could finally agree that the crack was real rather than some lingering, correctable error. It's worth sitting for these last few minutes with exactly what it means that James Webb, an instrument built and launched with the explicit hope, among many researchers who use it, of finally resolving this particular question, instead did the opposite, strengthening and confirming a problem so many had genuinely hoped might quietly disappear. There's a specific kind of scientific integrity embedded in that outcome, worth appreciating directly rather than passing over quickly. Nobody involved in that research manipulated their results to fit a preferred, more comfortable conclusion. Nobody quietly buried an inconvenient finding or waited for a more convenient moment to announce it. Researchers who had spent years hopping to find a mistake in their own earlier work instead published, honestly and directly, exactly what their new, more precise data actually showed, even though it meant confirming, rather than resolving, one of the most uncomfortable open problems in their entire field. That kind of honesty, choosing to report an uncomfortable, unresolved truth rather than a more comfortable, tidier story, is easy to take for granted, and worth naming directly as one of the genuinely admirable features of how modern science, at its best, actually operates. The universe did not owe astronomers a clean, simple answer, and when Webb's data made clear that no clean, simple answer was currently available, the field responded not by pretending otherwise, but by turning its full, considerable attention toward understanding exactly what kind of new physics might actually be required to explain what its instruments had genuinely found. There is a broader pattern worth naming here too, one that reaches beyond this single story about the expansion rate of the universe. Several of the threads we've followed together on other evenings, the CERN penguin decay anomaly still sitting just below the formal discovery threshold, the impossibly bright early galaxies Webb kept finding in nearly every deep field it examined, and now this persistent, unresolved tension in the universe's own expansion rate, share a common shape worth sitting with directly. Each one represents a moment where humanity's most sophisticated instruments, built at enormous cost and after decades of careful engineering, returned an answer more complicated, more uncertain, and more genuinely surprising than the simpler, more settled picture researchers had originally hoped to confirm. That pattern isn't a sign of science failing. It's closer to the opposite, evidence of instruments finally becoming precise enough, and data finally becoming abundant enough, to reveal genuine cracks in frameworks that had, for decades, seemed comfortably, perhaps even a little too comfortably, complete. Cosmology in particular has spent the past several decades in an unusual, historically rare position, a field where an enormous range of independent observations, from the detailed structure of the cosmic microwave background to the large-scale distribution of galaxies across billions of light years, kept fitting together with remarkable, genuinely impressive consistency inside a single, comparatively simple mathematical framework. That success created, understandably, a kind of quiet confidence throughout the field, a sense that the largest remaining questions were mostly matters of refining details rather than confronting anything genuinely foundational. The Hubble tension has done more than any single result in recent memory to gently, firmly puncture that confidence, replacing it with something researchers in the field now describe, with genuine and growing regularity, as a period of productive uncertainty, a phrase that manages to hold both the discomfort and the genuine excitement current cosmologists feel about the work still ahead of them. That work continues right now, tonight, in observatories and universities scattered across the globe, gravitational wave detectors, listening patiently for the next neutron star merger capable of adding one more data point to the still-developing standard siren technique, theoretical physicists refining early dark energy models, and testing them against an ever-growing body of precision cosmological data, and researchers like Adam Rees and Wendy Friedman continuing to push their respective measurement techniques toward ever greater precision, in the patient, ongoing hope of eventually understanding exactly what the universe has been quietly trying to tell them, in the specific, stubborn 9% gap between two otherwise extraordinarily careful, extraordinarily well-tested measurements of its own expansion. Thank you for spending this long, quiet evening with us here at Pale Blue Drift, sitting inside one of modern cosmology's most genuinely unresolved, most genuinely honest open questions, a puzzle James Webb was hoped to solve, and instead helped confirm as real. If slow, careful mysteries like this one, the kind without a tidy ending yet, are the sort of thing that helps your own mind settle into something calm and curious before sleep, there will be more evenings like this one waiting for you, more distant uncertainties, more patient, unresolved questions, more long, unhurried nights built for exactly this kind of stillness. For now, let the rest of tonight be simple. Somewhere above whatever roof is currently over your head, the universe continues expanding, at a rate nobody has yet managed to pin down with complete, unified confidence, stretching space itself a little further apart with every passing moment, indifferent to the careful disagreement still unfolding among the astronomers studying it. And down here, your own breathing can settle into its own quiet rhythm, unhurried, needing no resolution before sleep finally arrives. Sleep well.